Hi everyone, my name is Kang, and I'm very happy to be giving this short talk about my paper on the optimal indirect regulation of externalities. The motivation for this paper is the simple observation that policymakers often employ non-market policies, such as price and quantity controls, to regulate goods that cause externalities. Now, there are many examples of such non-market policies. For example, the sale and manufacture of psychoactive drugs is banned in many countries, while vaccines are frequently mandated by schools, employers, and government agencies. Even when goods that cause externalities are not outrightly banned or mandated, there can be price restrictions, such as a minimum price per unit volume of alcohol, as introduced in Scotland, Wales, and parts of Canada. There can also be quantity restrictions, such as one handgun a month laws introduced in parts of the United States. Now, at this point, you might be wondering why policymakers don't set a Pigouvian tax or subsidy instead. And indeed, if policymakers could measure the externality that each consumer generates and tax or subsidize that externality, then market efficiency can be restored. The problem, however, is that these externalities are heterogeneous, and it is often infeasible to measure how much externality each consumer generates. Take vaccines, for example. The positive externality that arises from vaccination depends on many things, such as where the consumer in question works, with whom they interact, and how likely the consumer is to take other actions like wearing a mask. As you can imagine, it is challenging for a policymaker to observe all of these things and set an individualized tax for that consumer. Instead, policymakers indirectly regulate the externality by regulating the good, such as mandating vaccines for everyone, or even just setting a uniform subsidy for vaccines. Unlike a Pigouvian tax, however, any indirect policy generates deadweight loss. And so two questions naturally arise. The first question is one of policy evaluation, namely how much deadweight loss does a given policy generate? And the second question is one of policy design, namely what is the optimal policy to indirectly regulate externalities? In this paper, I answer these questions by developing an approach that combines methods from the literatures on sufficient statistics and mechanism design. Let me now describe the model. There is a unit mass of risk-neutral consumers in the market for a homogeneous good. The good is produced competitively at a constant marginal cost, denoted by C. Now, consumption produces a heterogeneous amount of externality that cannot be measured. Consumers differ in two dimensions, namely a consumption type theta and an externality type xi. The consumption type theta determines the amount of utility theta times a function v of q that a consumer derives from consuming q units of the good. Each consumer can consume only non-negative amounts of the good up to some maximum quantity A. I also make the standard assumption that the function v is non-decreasing and strictly concave. One example of such a function is the quadratic function a times q minus half of q squared, which generates a linear demand function. I will come back to this example later on in this talk. On the other hand, the externality type xi determines the amount of externality that the consumer produces per unit of the good consumed. And so, if the consumer consumes 1 unit of the good, then he produces xi units of the externality. I will denote by g the joint distribution function of theta and xi, assumed to be absolutely continuous and supported on a two-dimensional interval. And finally, I will assume that consumer payoffs are additively separable in the total externality. In particular, the payoff that each consumer realizes is equal to theta times v of the quantity that he consumes, minus the payment that he makes, and minus the total externality produced by all consumers. Before introducing the social planners problem, let me first briefly comment on the first best benchmark. Suppose the externality that each consumer produces can be measured. In this case, the first best outcome can be attained by setting a personalized Pigouvian tax of xi. Under this personalized Pigouvian tax, each consumer thus faces a marginal price of C plus xi per unit of the good consumed. However, measuring and directly taxing the externality is often infeasible in practice. In all of the examples that I mentioned earlier, namely psychoactive drug use, vaccination, alcohol consumption, and gun purchase, the externality that each consumer produces is heterogeneous and difficult to measure. Even if the externality could be measured, it could be politically challenging to implement personalized pricing due to privacy concerns, for instance. And so this means that the first best benchmark is typically not implementable, and policymakers instead indirectly regulate these externalities by taxing consumption. Let me now describe the social planner's problem. The social planner chooses a mechanism consisting of an allocation function Q, which determines the quantity that a consumer with types theta and xi consumes, and a payment function T, which determines the payment that this consumer makes to the social planner. The social planner maximizes total surplus, which is equal to the total benefit that consumers derive from consuming the good, minus the total social cost incurred, which consists of the cost of producing the good and the cost of the externality. By the revelation principle, the social planner can restrict attention without loss of generality to incentive-compatible mechanisms. The incentive compatibility constraint specifies that each consumer can do no better than to report his types theta and xi truthfully. Given an allocation function Q, if there exists a payment function T such that the mechanism Qt is incentive compatible, then I will say that Q is implementable as a standard in mechanism design. It is now fairly straightforward to characterize the set of all implementable allocation functions. To do so, this lemma states that an allocation function is implementable only if it is almost everywhere equal to a non-decreasing function that depends only on consumption types. And this can be thought of as the analog of Meyerson's lemma in the present setting. Intuitively, this result holds because consumer payoffs don't depend on their reported externality types, and so there is no way to truthfully elicit these externality types from consumers. This result implies that the solution to the social planner's problem does not depend on whether consumers observe their own externality types. This is an important observation because even though we formulate externality types as consumers' private information, we don't actually think that it's practical for each consumer to necessarily know how much externality his consumption produces. This result tells us that the same analysis will hold regardless of whether consumers actually know their own externality types. A second implication of this result is that we can abuse notation slightly and write the allocation function as a function of only theta. I will therefore refer to the set of non-decreasing functions Q as a set of implementable allocation functions. In the context of the model, the two questions that I posed earlier can now be formally stated. And so first, what is the deadweight loss of any incentive-compatible mechanism? And second, given any subset S of implementable allocation functions, what is the optimal allocation function in S? That is, the allocation function in S that minimizes deadweight loss. If S is the entire set of implementable allocation functions, then the optimal allocation function is the second best allocation function. For the remainder of this short talk, I want to give an illustration of my results through the lens of a special case of the general model that I just presented. And so for this purpose, I want to focus on the case of linear demand. In particular, I return to the earlier example where the function v is quadratic, and I assume that the maximum quantity demanded A, which is also the maximum marginal benefit that a consumer receives, is sufficiently large relative to the social marginal cost that the consumer generates. This assumption ensures that the first best allocation for each consumer is interior, which simplifies the exposition of the analysis and results. Because the function v is quadratic, each consumer has an individual demand curve given by A minus P divided by theta. As you can see in this diagram, this generates linear demand curves that share a horizontal intercept equal to the maximum quantity demanded A. And these lines have vertical intercepts equal to theta times A. The linear demand assumption is a simple way to capture continuous demand for a homogeneous good and can be viewed as a local approximation in the spirit of Harburger who first used this approximation in the measurement of deadweight loss. Let me now show how the deadweight loss can be computed. We start by computing the deadweight loss arising from an individual consumer whose individual demand curve is the one shown here. To get this consumer's first best quantity, we plot the social marginal cost, which is a horizontal line here since the social marginal cost is constant. The point at which it intersects the demand curve gives the first best quantity. Suppose, however, that the consumer consumes a different quantity, which gives the second point shown here on this demand curve. And as Harberger showed, the resulting deadweight loss arising from this consumer will then be equal to the area of the shaded region shown here. And because this region is a right-angled triangle, its area can be easily computed and is equal to theta times half of the squared distance between the first best quantity and the actual quantity consumed. Now, by summing this expression over all consumers in the population, we therefore obtain the following proposition, namely that for any incentive-compatible mechanism, the deadweight loss is equal to half of the average squared distance between the first best allocation function and the allocation function in question, weighted by consumers' consumption types theta. And while this is a relatively simple result, let me now argue that it is useful by connecting it to regressions. And so to illustrate this, consider the question of what the optimal linear tax is. Since individual demand curves are linear, any allocation function that can be implemented by a linear tax tau can be written in the form a minus c plus tau divided by theta. And we let S denote the set of all such allocation functions. We then consider the regression of the first best allocation function onto this set S. Explicitly, the regression equation that I want you to consider has the first best allocation on the left-hand side and an allocation function parametrized by the linear tax tau on the right-hand side, as well as a regression error term, epsilon. We can remove the common terms a and c on both sides of the equation to obtain the simplified regression equation, where on the left-hand side, we have the ratio of externality types xi to consumption types theta, and on the right-hand side, we have tau times 1 over theta. And to perform this regression, we plot xi over theta against 1 over theta. And we then estimate the best fit line that passes through the origin, but the distance of each point to the best fit line is weighted by consumption type theta. Now, there are two things I want to point out about this regression. The first thing to point out is that the sum of squared residuals, weighted by theta, is equal to 2 times the deadweight loss. This observation arises immediately from the previous proposition, and it tells us that the total amount of error in this regression has economic meaning. It also implies that the gradient of the best fit line that we estimate from this regression gives the optimal linear tax, that is, the tax that minimizes deadweight loss. The second thing to point out is that the optimal linear tax can be explicitly evaluated here using standard regression formulas. These formulas tell us how to project the data points onto a parametrized family of functions. In this case, when the best fit line has to pass through the origin, the formula for the optimal linear tax is equal to the average ratio of xi to theta divided by the average reciprocal of consumption types theta in the population. And this recovers the familiar result of Diamond, who showed that the optimal linear tax is equal to the average externality weighted by the gradient of each consumer's demand curve. Now, the upshot of our mechanism design analysis is that we can generalize this approach to allow for nonlinear taxes. In particular, we can derive the second best allocation function by regressing the first best allocation function, but now onto the set of all implementable allocation functions. Again, the regression loss function here is half of the sum of squared distances weighted by each consumer's consumption type theta. And because the set of implementable allocation functions is equal to the set of non-decreasing functions, this means that the second best allocation function is the isotonic regression of the first best allocation function on consumption types theta. And so what is the second best allocation function? Suppose that conditional on consumption types theta, the expected first best allocation as a function of consumption types theta is as shown. The second best allocation function can then be derived by ironing regions over which the expected first best allocation function is non-monotone. Ironed regions must satisfy an equal weighted areas condition where the two areas highlighted, weighted by consumption types theta, must be equal. And so formally, this result can be described mathematically as follows. And here, the optimal allocation function is unique, and uniqueness also holds for the optimal allocation function in any subset of implementable allocation functions. Also, notice that although the construction of the second best allocation function uses ironing, it is different from ironing in other mechanism design problems where the marginal revenue curve is ironed. Here, the expected first best allocation function is ironed instead. The proof of this result uses the fact that, similar to how we obtain the optimal linear tax, this regression can also be solved by finding the weighted least squares projection of the first best allocation function. In the paper, I show that this projection operator is given by the ironing procedure in the statement of this proposition. To summarize our takeaways from this illustration, I now explicitly answer the two questions that we set out to answer. First, the deadweight loss of any incentive-compatible mechanism is equal to the weighted average distance between the first best allocation function and the allocation function in question. Second, in any subset of implementable allocation functions, the optimal allocation function is the best fit allocation function from a regression of the first best allocation function onto that set. In particular, the second best allocation function can be determined by an isotonic regression. While I have argued in this talk that these statements hold in the case of linear demand, the paper also shows that this regression approach holds for general demand. This is done by generalizing the regression loss function from weighted squared distance to weighted Bregman divergence and characterizing the resulting projection operator. To conclude, this paper develops a regression approach to indirectly regulate externalities. Using this approach, deadweight loss is equal to the residual from the regression in question, and the optimal indirect policy is obtained by characterizing the projection associated with this regression. The results of this paper have economic implications. And in the paper, I show that these results imply that non-market policies, such as price and quantity controls, can be optimal. I also show how to implement optimal allocations through nonlinear taxes and how these nonlinear taxes themselves can be estimated by regression. And finally, I show how the results of this paper also have empirical relevance through an empirical application to the regulation of automobile externalities via the taxation of vehicle miles traveled. That brings me to the end of my talk. Thank you so much for watching.